Alrighty, everybody, this is going to be third time's a charm, hopefully. So we are going to be learning about thermochemistry tonight in our online notes. I know we haven't done it in a while, so let's get to it. So we're going to be talking about thermochemistry. We're going to start with some review and an introduction to new material. But first of all, we need to talk about an error of mine, and we're going to make a correction for it. So let's start with that correction. Way back ago, long ago, in Unit 4, we were introduced to the idea of heat in the form of Q equals mc delta T. Now, I called this Hess's law. This is not actually correct. Q equals mc delta T is an equation for heat, but it is not actually Hess's law. We're going to be learning about the real Hess's law in this unit. Now, I knew about halfway through Unit 4, when I was talking about Q equals mc delta T, I figured out that it was not actually Hess's law, but I decided that fixing the mistake in the middle was only going to confuse you, and so I chose to fix it when I got to the real Hess's law, which is now. And so now I'm fixing it. Everything you learned about Q equals mc delta T is still correct. The name is just wrong. Okay, so it doesn't change anything that you learned about Q equals mc delta T or Q equals n delta H or anything about our heating curves and cooling curves. That's all still true. It's just that it's not called Hess's law. And in fact, there really is no real name for that equation. So we're just going to keep calling it Q equals mc delta T or Q equals mcat, and we're going to leave it at that, and we're going to now learn about the real Hess's law and call that Hess's law. And I apologize for any confusion, you guys. I really do. I'm human, I'm fallible, and this is one of probably my bigger mistakes this year. So I apologize, and hopefully we can all move on together and be okay about it. Okay, so let's talk about thermo. Thermochemistry is the study of energy changes occurring during chemical reactions and changes in state. So every substance that we have has an amount of energy stored inside of it. This energy, which is stored in the chemical bonds of a substance, is called chemical potential energy. Now, during a chemical reaction, a substance is transformed into another substance, and this other substance has a different amount of chemical potential energy, because each individual substance has its own chemical potential energy. And so the excess chemical potential energy is then transformed into work, heat transfer, or a combination of both. So that's what we're talking about here, is we're looking at substances changing into other substances, and the difference in their chemical potential energies is what we're going to be looking at. So heat, which is represented by the letter Q, is the energy that is transferred from one object to another due to the difference in temperature. Heat always flows from the warmer object to the cooler object, and if two objects are touching, energy will continue to transfer from the warmer object to the cooler object until the two objects have the same temperature. Just like when you learn in biology about diffusion and how you're going from a more concentrated to a less concentrated solution. So it's the same idea with heat. And thermochem is all about heat. So we've got some terminology that we need to talk about when we're talking about thermo. And the first one is the system. And this is the part of the universe on which you're focusing your attention. So this is the actual reaction, the very specific nitty-gritties, the reaction. The part of the universe that we're focusing on, our focal point, is called the system. We then have the surroundings, and this is the rest of the universe, or more specifically, the region in the immediate vicinity of the system. So if you have system and surroundings together, you have an entire universe. The system is the very specific part that you're focusing on, and the surroundings is everything else. When we're talking about heat, we have two different processes that we talk about. We have exothermic processes, which releases heat to the surroundings, and then we have endothermic processes, which absorb heat from the surroundings. So endothermic processes absorb heat from the surroundings, or they require heat. Exothermic processes release heat to the surroundings. Everybody got that? Okay. You may want to jot this down. Just putting it out there. So let's talk about specific heat again, because we have already covered that, but it was a while back. So let's have a recap. So the first thing is that the specific heat is the amount of heat required to raise the temperature of 1 gram of a substance 1 degrees Celsius. And we give that as an equation, Q equals mc delta T. Now, Q that we measure is actually the Q of the surroundings. Okay, does that make sense? We can't actually measure the heat of the specific reaction. That's really hard to do. So we measure the Q of the surroundings. That's where we get our mass, our delta T and that kind of stuff. That is of the surroundings, because we can't actually measure the heat of the specific reaction itself. Substances with low specific heats are much more affected by heat than those with high specific heats. So what this means is that if you have a low specific heat, say something less than 1, you are going to be affected by temperature more than something with a high specific heat, like water, for example, with a specific heat of 4.18 joules per gram degree Celsius. So let's say a metal has a specific heat of 0.90 joules per gram degree Celsius, and water has a specific heat of 4.18 joules per gram degree Celsius. The metal is going to heat up faster or more than water, given the same amount of energy being put towards it. So heat energy. So the lower the specific heat, the more easily it is affected by temperature. Calorimetry is the precise measurement of the heat flow into or out of a system. So when we're studying systems and enthalpy and thermo like this, we usually use something called calorimetry. And heat released by the system is equal to the heat absorbed by the surroundings. Like I said, you have a system and you have your surroundings, you have the universe. So if something is lost by the system, it has to be gained by the surroundings. We're not losing or creating anything. You can't destroy it or make it up from fresh. So this is the whole idea of the conservation of energy. Anything lost by the system has to be gained by the surroundings. And if anyone's wondering out there whether or not you're ever going to use this in your real life, I used it in my real life. I used calorimetry as a way to calibrate the reactor when I worked there. So I actually used this science that I learned back in high school. I applied it to my everyday job when I was at the reactor, which was kind of cool. So there. All right, let's talk about enthalpy, or H. Enthalpy is the heat content of a system at constant pressure. Heat absorbed or released by a reaction at constant pressure is the same as the change in enthalpy, or the delta H. So everything that we do here, we're either going to be measuring it in terms of Q or in terms of delta H. But it's called enthalpy, or the heat content of a system. Exothermic reactions have a negative delta H, whereas endothermic reactions have a positive delta H. Okay? And this is going to make sense here in a second. When you have Q systems equal to negative Q surroundings, okay? Remember what we said about the universe, and if something is gained or lost, if something is lost by the surroundings, it has to be gained by the system, or if something is gained by the system, it has to be lost from the surroundings. So if your system is positive, your surroundings is negative. Now, we measure surroundings. So what does that mean then? If Q system is equal to delta H, which is therefore equal to negative Q surroundings, delta H is going to be equal to negative mc delta T. Because Q surroundings is equal to mc delta T, so negative Q surroundings would have to be equal to negative mc delta T. Which is why when you have an exothermic reaction, which has a change in temperature, and you're measuring that change of temperature, you get a negative number, because you're actually measuring the temperature of the surroundings. The heat is being given off to the surroundings. That's why exothermic reactions, the temperature goes up. Heat is being gained by the surroundings or released from the system. So you get a negative delta H for exothermic reactions and positive delta H for endothermic reactions. Okay, so we've got Q systems and Q surroundings and delta H's, oh my. So let's try and get this all straightened out, and hopefully this page will help straighten it out for you. But experimentally, we measure Q surrounding, as measuring the Q system is incredibly difficult. It is a very small part of the universe, after all. So, delta H is always calculated in terms of Q system, as the heat of enthalpy is of the system, not the surroundings. So we have a problem here. Delta H is always calculated in terms of Q system, but we always measure Q surroundings. So we have to be able to relate that somewhere which is why our delta H is equal to negative Q surroundings. Since we normally calculate Q surrounding when calculating delta H, we need to calculate negative Q system. Oh, that's a mistake, guys, and this is seriously like the third time I've done this, so I am going to go, we normally calculate Q system when calculating delta H, so we have to do surroundings. I'm sorry, I know that this is annoying, but I can't do this over again. This is like my third time. Okay, let's get back here. So, since we normally calculate Q system when calculating delta H, we need to calculate negative Q surrounding, as Q system is equal to negative Q surrounding, right? I've said that a couple times, now you've seen it in writing. So, this is why delta H will be negative for exothermic reactions and delta H will be positive for endothermic reactions, because our delta H has to be calculated in terms of negative Q surroundings, which is what we measure, so our exothermic reactions are negative delta H's. I really hope that that clears it up. If not, we'll talk about it a lot tomorrow. So, let's keep going. All right, let's look at an enthalpy question. When 25 milliliters of water containing 0.025 moles of hydrochloric acid at 25 degrees Celsius is added to 25 mils of water containing 0.025 moles of sodium hydroxide at 25 degrees Celsius in a calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules during the reaction if the final temperature is 32 degrees Celsius. And here they want you to assume that the density and specific heat of both solutions is 1 gram per mil and 4.18 joules per gram degree Celsius, respectively. Okay, so there's a lot of information there, so let's figure out what we need. So we know that Q system is equal to delta H, which is therefore equal to negative MC delta T, or delta H is equal to negative MC delta T if we want to calculate the enthalpy, which we do. So we're going to need to find the mass, the specific heat, and the change in temperature. Now we had 25 grams of water with hydrochloric acid in it, and 25 grams of water with sodium hydroxide in it. So our mass should be 25 plus 25. They told us that our specific heat is 4.18 joules per gram degree Celsius, and we know that the final temperature was 32 degrees Celsius when the initial temperature was 25 degrees Celsius. So when we plug this all into the equation, we get an answer of delta H is equal to negative 1,463 joules, but they wanted the answer in kilojoules, so we're going to need to divide by 1,000 to get an answer of negative 1.46 kilojoules. Now this enthalpy, since it's negative, means that this is an exothermic reaction. Okay? Not too bad. Not too hard. Now, one thing that I want you guys to look at, though, is the fact that in this equation, we talked about two things that we never did anything about. Moles. Okay? Now, that's because the delta H's that we're calculating are for the reaction as it's written, and so we don't need to actually factor in the number of moles. Okay? We're going to talk about this a little bit more in the future. But Q is equal to, delta H is equal to negative 1.46 kilojoules. So let's talk about chemical reactions and enthalpy change. In chemical reactions, enthalpy change can be written as either a product or a reactant, dependent upon if the reaction is exothermic or endothermic. So if you've got an exothermic reaction, heat is being given off, which is enthalpy change, so our delta H is going to be a product, whereas in endothermic reactions, you have to put heat into the system in order for it to actually work, so enthalpy would be written as a reactant. So for example, calcium oxide plus water makes calcium hydroxide plus 65.2 kilojoules. In this case, our kilojoules, or energy, is a product, which means that this is an exothermic reaction, which means that our delta H is going to be negative. So this can also be written as calcium oxide plus water makes calcium hydroxide with a delta H of negative 65.2 kilojoules. Okay? So let's practice this. If you have, oh, and I saw this last time and I forgot to change it. Sorry, guys. This is just the worst. So if I have a reaction where I have 2 sodium hydrogen carbonates plus 129 kilojoules, making 2 sodium carbonates plus water plus carbon dioxide. This is our reaction. Now, this has an enthalpy. The enthalpy here was a reactant, which means that our delta H is going to be positive. So our reaction as written is 2 sodium hydrogen carbonates making 2 sodium carbonates plus water plus carbon dioxide. And this is a delta H of positive 129 kilojoules, meaning this is an endothermic reaction. Now this is a decomposition reaction, which it makes sense that it actually requires energy in order to happen because of the way that the reaction is going. You're going from one thing to many things. It's going to take a little bit of effort. So, and now that I'm looking at it, I don't even think this is a balanced reaction. It's not. Oh my gosh, you guys, I am just having the worst day. This should be a subscript 2 right there. I'm sorry. So sorry about this. I couldn't be sorrier. I kind of hate myself right now, but I've been working on this for a really long time and I don't want to do it again. So there we go. That's a balanced reaction. Okay. So if the question now, this is a proposed reaction for you. So the question then is, given the reaction above, what is the enthalpy change for 2.75 moles of sodium hydrogen carbonate? Now, I mentioned earlier that the delta H is written as just plain old kilojoules, and that's because this is the delta H for the reaction as written. Now, the reaction written here has us having 2 sodium hydrogen carbonates, and if any of you remember, the 2 actually stands for 2 moles. So then the question is asking us, well, what if you had 2.75 moles? What's the enthalpy change there? And so here we just need to do a little bit of unit conversions and stoichiometry. So delta H would be then equal to 2.75 moles of sodium hydrogen carbonate multiplied by the fact that there are 129 kilojoules for every 2 moles of sodium hydrogen carbonate, which is going to be equal to a delta H of 177.375, which is going to be a delta H of 177 kilojoules. Now this makes sense. If you have more moles, your delta H should be larger, and so we go from 129 kilojoules to 177 kilojoules. Right? Not too bad. So heat and changes of state. So right there we had a heat of reactions. Now let's look at heat and changes of state. So I drew this pretty picture for you guys. And we talked about heat and changes of states when we drew our heating and cooling curve. So let's talk about it just really quickly. We go from low enthalpy to high enthalpy, and or solid to vapor state. And so when you're going from a solid to a liquid, you have a positive delta H of fusion. And when you're going from a liquid to a vapor, you have a positive delta H of vaporization. And going in the alternate direction from high enthalpy to low enthalpy, you get a negative delta H of condensation from vapor to liquid, and a negative delta H of solidification from liquid to solid. So these delta H's are going to be the same values, just different signs. These are also called the molar heats of whatever phase change we're looking at. The molar heat of fusion, the molar heat of vaporization, and so on and so on. And it's the amount of heat absorbed or lost by 1 mole of a substance as it changes phases. And that's specifically 1 mole. And because it's for just 1 mole, the units are always in kilojoules per mole, not just straight up kilojoules. And that's what I just said straight up. So let's talk about phase change calculations. We can use these standard heats of phase changes to calculate different things. The amount of heat required to perform a phase change, the grams of substance that will melt given a specific amount of heat, etc., etc. So let's look at the question that we have here. How many grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat is added? And we're given the delta H of fusion, or the melting, as 6.015 kilojoules per mole, and the molecular weight of water as 18.015 grams per mole. So we're always going to start with the thing that we have 1 unit of, so 2.25 kilojoules. And we're trying to figure out grams, so we need to go from kilojoules to moles and moles to grams. So kilojoules to moles, moles to grams. I think you know where I'm going here. So we're going to start out, as we should everything, with a balanced reaction. Since the delta H of fusion is positive, that means it's a reactant. It's an endothermic reaction. So we're going to have solid ice plus 6.02 kilojoules per mole can get us to water. And then the mass of ice can be found by taking the single unit, 2.25 kilojoules, multiplying it by kilojoules per mole, and then multiplying it again by moles per gram, getting a total of 6.74 grams of ice. So if you add 2.25 kilojoules of heat to a bunch of ice, only 6.76 grams will actually melt. Cool, huh? Alright, so we talked about heats of reactions, heats of formation? No. Heats of phase changes. Now we're talking about heats of solution. So during the formation of a solution, heat is either released or absorbed. And when we're talking about solution, the enthalpy change is called the molar heat of solution, and it's represented by the heat released or absorbed caused by the dissolution of 1 mole of a substance. When we're talking about solutions, we're talking about aqueous solutions here, so some ion dissolved in water. So this is the type of reaction that you actually see occurring in disposable hot or cold packs. So where a hot pack is formed from an exothermic reaction and a cold pack is formed from an endothermic reaction. So those things, that when you crack them, you're actually cracking open some sort of capsule that has a chemical in it that is going to go into the water that you have already in that packet into solution. And then as it dissolves in there and disassociates or goes through a dissolution, it either gets hot or cold depending on whether it's an exothermic reaction or endothermic reaction. Pretty cool, huh? So, let's talk about Hess's law. The real one, people. Sometimes it's hard to measure the enthalpy change for a reaction. Either the reaction might take place too slowly, or the reaction might be an intermediate step in a series of reactions, so you can't actually identify the specific reaction you're looking at, or many other reasons. And this is where Hess's law comes in. It allows scientists to measure the heat of a reaction indirectly. So Hess's law, or Hess's law of the heat of summation, states that if you add 2 or more thermochemical equations together to give a final equation, then you can also add the heats of reactions of those equations to give a final heat of reaction. So if you can go through and make different equations, add them together to get the final product equation that you want, you can do the same with their heats of reaction to get the actual heat of reaction of what you're looking at. So let's look at this. Graphite is actually a more stable form of carbon than diamonds. Luckily, though, this reaction takes millions and millions and millions of years for diamond to convert into graphite. So we might want to know what the heat of the reaction is. But it would take too long for us to actually measure this because it's going to happen over millions and millions and millions of years. So we can use Hess's law to determine what that heat of reaction would be. And what we're going to be doing here is we're changing carbon from diamond into carbon graphite, and this is the overall equation that we're going to be looking for. But I don't have any values of delta H for this. I do have delta H of formations of carbon dioxide from graphite plus water, making a delta H, having a delta H of negative 393.5 kilojoules. So we're taking graphite plus oxygen and making carbon dioxide. Or we can take diamond plus oxygen and make carbon dioxide, and that has a delta H of negative 395.4 kilojoules. Now we're trying to get a reaction of diamond to graphite, but right now the only 2 equations we've been given have both graphite and diamond as reactants, and we need graphite to be a product. So the way that we can do this is by flipping the equation, turning it around, reversing the reaction, making it go from carbon dioxide to graphite and oxygen. If you do this, though, you have to flip the sign, too, of the delta H, because the reaction is going in a different direction. So we can do this, and now our 2 reactions that we have are diamond plus oxygen making carbon dioxide with a negative delta H of negative 395.4 kilojoules, and carbon dioxide going to graphite and oxygen with a positive delta H of 393.5 kilojoules. Now we still don't look like we have this equation. We need to add these together, but we've got a lot of extra stuff going on. So if you can cancel out something that is on both the product side and the reactant side, it's going to go away. So if we look, we can see that we have oxygen as a reactant in this equation and a product in that equation, so it cancels out. We also have carbon dioxide as a product here and a reactant there, so that cancels out. Now, when we add these 2 together, we have diamond going to graphite, which is exactly what we wanted to do. So our delta H, since we just add these 2 together to get our equation that we're gearing up for, all we need to do is add these two numbers together, which gives us a grand total of negative 1.9 kilojoules. Okay? So all we're doing here is manipulating equations and moving them around so that we can get the equation that we're looking for. Now you can also see this pictographically or pictorially by looking and seeing that diamond plus oxygen makes carbon dioxide, and it has a delta H of this, and graphite plus oxygen makes carbon dioxide, or in this case when we flipped it, carbon dioxide can go to graphite plus oxygen and it has this delta H. And so all we're looking for is this missing delta H. And we can do that by just adding those two numbers together, which you get negative 1.9 kilojoules. Now you'll notice that that question mark disappeared. I went all fancy on the animations here, guys. I worked super hard. I wanted to make you guys proud. So if this helps you to explain things pictorially, great. You can make your own pictures for any of these Hess's law equations. Alright, so let's practice this. What is the enthalpy change for the formation of carbon monoxide from its elements, carbon and oxygen? So we're looking for carbon graphite plus a half O2 making carbon monoxide. And we're looking, this is the enthalpy change of formation, which is why we have to use this delta H. In the enthalpies of formation, you only get to make 1 mole of the product. So we're given these two known enthalpies. Graphite plus oxygen makes carbon dioxide, and carbon monoxide plus a half of oxygen makes carbon dioxide. And they both have their own enthalpies. Now again, we want our reaction to look like this, so we need carbon monoxide as a product, but here it's a reactant. So we're going to need to swap and flip this equation, which means we're going to need to change and reverse our delta H as well. So we can do that, and now we have carbon dioxide making carbon monoxide plus a half O2, and we flip the signage on our delta H. So let's try and cancel some stuff out, because we need graphite plus a half O2. And right now we have graphite plus oxygen. But I have a half O2 on my reactant, or on my product side here, which I can cancel this 1/2 O2 with this oxygen, but only half of it. So I can cancel that out and make a half O2, which is exactly what we wanted, so that's great. And then I have carbon dioxide over here as a product and carbon dioxide as a reactant. So now I have carbon graphite plus a half O2 making carbon monoxide, which is exactly what I wanted to do. And so since I just added these together, all I have to do is add my delta H's together. And we get a negative 110.5 kilojoules. Not bad at all. And again, we can see what this looks like pictorially, and you just solve for that difference there. Okay? So I want you guys to take a second and practice. And keep in mind that when we reversed the reaction, we had to change the sign of the delta H. Now, if you have to multiply or divide the reaction in order to make it work, you're going to have to do the same to the delta H again. So I want you to figure out what the delta H is for the reaction of 2 phosphoruses plus 5 chlorine gas making 2 phosphorus pentachloride. Given that phosphorus pentachloride makes phosphorus trichloride in chlorine gas with a delta H of 87.9 kilojoules, and 2 phosphoruses plus 3 chlorines can make 2 phosphorus trichlorides with a delta H of negative 574 kilojoules. So I want you to take that and try and make it work. So go ahead and pause the video and work on this. Now let's go through and figure it out. Now we see that we have 2 phosphoruses and 2 phosphoruses both as reactants, so that's good. And we have over here, we have 2 phosphorus pentachlorides as a product, but over here we have 1 phosphorus pentachloride as a reactant. So we're going to need to reverse this reaction to make a reactant into a product. But this also has 2 here, so we're going to need to multiply this also by 2, which means we need to multiply our delta H by 2. So we've got that going on, which when you spread out those 2's, this is going to become 2 phosphorus trichloride plus 2 chlorines, making 2 phosphorus pentachloride, and a new delta H of negative 175.8 because we had to reverse it, so that becomes negative, and you times it by 2 to get the negative 175.8. Now I'm going to just bring the 2 phosphoruses and 3 chlorines down so that we have everything nice and neat and packed in. Now let's see if we can cancel anything out. And I see a phosphorus trichloride as a reactant and as a product, so that's going to cancel out. Now let's look back at our original equation and see what we've got on the product side. On both of these, we just have 2 phosphorus pentachloride. So that's good. That's exactly what we wanted. And now we have 2 phosphoruses, and we have 2 chlorines and 3 chlorines, which if you add those 2 together, you're going to get 5 chlorines, which is exactly what we wanted. So all we had to do was add those 2 equations together to get our final equation. And so all we're going to have to do is add these 2 numbers together. Negative 175.8 plus negative 574 gives us a total delta H of negative 749.8 kilojoules. Alright, it's just manipulation and moving things around, and I actually think it's really fun. So that's the majority of Hess's law there. Now let's talk about some different things, like the standard heats of formation. Scientists use something called standard states, which are conditions of 25 degrees Celsius and 1 atmosphere, to compare the enthalpy changes at different conditions, because we like to be able to compare things. Because what does it matter if the delta H there was negative 749.8 kilojoules? What does that matter if we don't have anything to compare it to know if that's high or low or whatever? So the standard heat of formation, or the delta HF of a compound, is the change in enthalpy that accompanies the formation of 1 mole of a substance from its elements in their standard states. So delta H's of formations, it's very important that you know that those are from elements in their standard states. And the delta H of formation of a free element or a natural element is arbitrarily set at 0, meaning that it doesn't take any energy to form these free elements or natural elements, which kind of makes sense, because if it's already occurring in nature like this, it shouldn't require any energy to make it. And we can calculate the delta H, so the standard enthalpy of reaction, to be equal to the sum of the delta H of formation of the products minus the sum of the delta H of the reactants, delta H of formation of the reactants. So when we do calculate the standard heat of reaction, we're going to start off with the balanced chemical equation, because that's what we always start out with. Then we're going to find and add the delta H of formations of all the reactants, taking into account the moles of each. So trying to figure that out. Then we're going to find the delta H of formation of the products, the same as in step 2. And then we're going to solve for the delta H of the reaction, or the standard heat of reaction, by, again, delta H is equal to the sum of delta F of the products minus the sum of the delta F of the reactants. Okay, everybody clear on that? Okay, so let's do an example. What is the standard heat of reaction, the delta H, for the reaction of carbon monoxide with oxygen to form carbon dioxide? And I've given you the enthalpy of formation of oxygen, carbon monoxide, and carbon dioxide. So, we're going to need to use those in order to figure out the delta H of reaction. But first, we have to start out with the balanced reaction. So 2 carbon monoxides plus 2 oxygens will make 2 carbon dioxides. Okay? So we start out with that balanced reaction. Now we need to find the delta H of formation of the reactants. So let's look at the delta H of reactions, of the reactants. So the delta H of formation of a reactant, if we look at carbon monoxide, we have 2 moles of carbon monoxide, but we know that there's a delta H of formation for carbon monoxide is negative 110.5 kilojoules per mole. So we plug that in there, and that means that we have a total of negative 221 kilojoules for the formation of carbon monoxide. Now what about the formation of oxygen? We have 2 moles of oxygen, but the delta H of formation of oxygen is 0. Why? Because oxygen found in nature is just oxygen. It's a free element. It's in its natural state, so it has delta H formation of 0. So that was pretty easy. Now let's look at our products. We have 2 moles of carbon dioxide, so we're going to have 2 moles of carbon dioxide and multiply it by its delta H of formation to get negative 787 kilojoules. So then the delta H of the reaction, the standard heat of reaction, is going to be the sum of the products minus the sum of the reactants. So we're going to have to add our product, which there's only one, and subtract it from the sum of our reactants. So negative 787 minus negative 201 plus 0. So that's a total of the standard heat of reaction is negative 566.0 kilojoules. Pretty cool. Now you can kind of check to see if this makes sense, because the delta H is negative, which means that it's exothermic, which makes sense since combustion releases heat. And this would be considered a combustion reaction because you've got oxygen right there. And you're making carbon dioxide. Okay? Now, what is the difference in delta H of formation and delta H? And I've got to tell you, it's all in the moles. So, if we look here and we have 2 carbons plus 2 oxygens making 2 carbon dioxides, there are 2 different numbers here. We have the delta H and the delta HF. Delta H of formation is, again, this is the molar delta H of formation. And so it is the molar enthalpy of formation. You're only allowed to make 1 mole of your product, your CO2. So it would be 1 carbon plus O2 making 1 carbon dioxide. So that's where that number comes from, and it's a standard. Delta H looks at the reaction as it's written, which there are 2 moles of carbon and 2 moles of oxygen and 2 moles of carbon dioxide. So you're going to multiply it by 2 to get your delta H. The difference is in the moles. Now, if we do the same thing and look here over at 2 carbon plus 2 oxygen making 2 carbon monoxide plus 2 oxygen, again, you've got a delta H of formation, but you've got 2 moles of each, so you have to have the delta H multiplied everything by 2. Same thing of trying to go from 2 carbon monoxide plus oxygen to 2 carbon dioxides. Here, we don't actually have a delta H of formation here, so we just have a delta H, which we got from the difference of this delta H and this delta H. Okay, we're going to be working a lot on this. I know that this was hard and it's kind of a hard concept to talk about, but I wanted to give you a really quick overview of everything so then we can get down into the nitty-gritty of each individual thing. Delta H's of formations, delta H's of reactions, delta H's of solutions, Hess's law, and all that, and we can get down to the nitty-gritty of it. So, I look forward to seeing you guys tomorrow. I hope that we can have fun and start doing this. All right, thanks, guys. Have a good night. Oh. Okay, now I don't know how to get this to stop recording. Oh, there we go.